Good morning, my fine young Procyon lotors. Flat mirrors are kind of flat. They're not that interesting to do, though they're those cool special effects. We're going to look at curved mirrors. First thing we're going to do is draw a curved mirror on here. We need to start with a horizontal line, nice and beefy and drop shadowy, and we're going to add a curved mirror, and that's going to be this arc tool right there. Click on it, hold the shift key down so you get a square shape to the curve, a circle, not a weird distorted oval like that. We want to move these little yellow pips. I'm going to move the one right here to right on that horizontal vertical line, and then I can move the other one and know that I've got them even with each other. Now we want to embiggen it a bit larger, and we'll center it on this line. So I'm going to click, and you see that little horizontal line that just appeared? Tells me I'm lined up, but not quite, so I'll just nudge it a bit. There we go. I'm lined up, and beefify it, shadow it. Now we need to locate the center of this curvature. If we'd drawn it with a protractor, where is the center? Well, it's right between these two lines, right there. So what am I going to do to locate that center? I'm going to go up here. I'm going to get a shape, and I'm going to just draw it right in there, like that. With a little cleverness, it will tell us. You see that? It's telling you it's been lined up on the center of that circle. And we can confirm it in just a minute here. Watch. When I click on this, you can see I'm lined up in the center. That's our center. We're going to mark another spot using one of these. It's a different symbol, and it's called the focus. And the focus is exactly halfway between the center and the mirror. Let's take a count. 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 and a half. So 5.5 would be the focus. 1, 2, 3, 4, 5. And a half. We're going to label the parts now. Give yourself lots of room. Set it up to maybe 30-point font. And this is going to be PA, which is the principal axis. Principal axis. Over here, that's called the center of curvature. And this is the focus. And there's one more part that I don't refer to much, but other teachers may. Just in passing, we can talk about. You've heard this term before, vertex, in math class. The vertex is over here. Okay? It's where the mirror and the principal axis combine. Right? Those are parts of the round mirror. Now we want to see what the rays of light would do when we send them into this mirror. You need to be able to label one of these mirrors with basically saying the principal axis, the center, and the focus. In reality, it's that easy. All you have to remember is put the focus halfway between the center and the thing. So you can even write that in here. There you go. Let's take a look at the rules governing the mirror. I put the center on here, and I've moved my focus to halfway between the mirror and the center. So you do the same thing. What beams of light can enter the mirror? Any beam of light we so ever want can enter the mirror. But any old beam is going to require us to get a protractor and carefully lay everything out. What we want to see is if there's a short form, a simpler way to make this easier than tracing rays willy-nilly all over. And there are. We would discover them experimentally in school, but we can't now. So we'll do it straight geometrically. What if I send a ray in straight to the mirror? What would it do? If you were in the middle of a round barn, completely round, and you kicked a ball straight at the wall, what do you expect it to do? Let's zoom in and have a look. I think most of you realize it'll come straight back. Why is that? Well, what angle does it hit the wall at? When you look at this, can you not see that this ray is a spoke? It's coming in at 90 degrees to the surface. The spoke in a bicycle wheel intersects the surface at 90 degrees. The wheel on an old ship, the peg sticking out of the wheel, hit the surface at 90 degrees. The CN tower points straight towards the center of the Earth, but it's 90 degrees straight up from the surrounding land. Because this is a 90-degree intersection, it's just like a plain old kick, straight into the wall, and it will come straight back out here. And a lot of textbooks will just slide it over a little bit to make it clear to you that that ray is there and it's coming straight out from the other one. Okay, didn't quite get it there. You get the idea. So rule 1 is there we go. No protractor needed. As long as you know where the center is, you can do this. Rule 2. Dead easy. Put the focus halfway to the mirror. Now, which way can we send the beam in? I'm just telling you what to do, right? There's no discovery here. What if we sent a beam in parallel to the mirror? Because parallels are really easy to do in a lab as well. No protractor needed. Where do you think it should go? Well, I think most of you realize if I said to you, does it go up? Does it go straight back? Does it go down? You know it's going to go down somewhere. The question is where? And that's what we're about to find out. If I put that mark there and I turn it gray and we look at the surface again, is this not, once again, a diameter or a radius? It's a line through the center of the circle. And that line going through the center of the circle guarantees hits the rim at 90 degrees. It has to. So you put this on. And basically, I can even extend this line a little bit. That's 90 degrees. Now, what are the rules of reflection? Isn't a 90-degree line the normal to the surface? Why, by Jove, so you're right. It is the normal. Perpendicular. 'Tis the 90 degrees. Why, it's orthogonal to the other one is well, yes, James, I know you've got it now. So, this is the angle the beam struck on its way in. Well, isn't the rule of reflection the angle you went in on should be the angle you came out when you hit this flat spot? Think of that flat spot as like a disco ball with all those tiny mirrors attached to it. You're seeing a local flat spot. So how do we make the equal and opposite angle? Remember my thing I said about counting squares? This ray is 3 squares up here. If I want to come down on the same angle, I go 3 squares down. Easier to show than speak. Tell me if you think the angle from this dotted gray line is the same when I do this. When I go right over here, did I just draw the same angle? Not quite, because I did it from here. That's where I counted from. Comes very close. These are scale diagrams, by the way. They're not sketches, so they're pretty sensitive to mistakes. But these two angles are the same. I'm off a little bit in my drawing, so I'm going to force it right through the focus. So rule 2 is and it turns out it works in both directions. Because why wouldn't it? If you're playing kick with somebody and they hit it and it came this way, then going backwards will do the same thing. There you go. And this rule works both ways. I'm going to move it down there. A lot of teachers teach it as 2 separate rules, but it isn't. It's just the rule works in both directions. The last rule is hardly ever needed. I'd say less than half of teachers use it, but some do. And that last rule is this one. What happens if you sent a beam in straight for the center of the mirror there? Not the center as in the geometric space, but the actual vertex. You go right in for the vertex of that mirror. Well, once again, this principal axis is sitting 90 degrees to the little tiny flat surface there. So this should be just like it was a flat mirror. Right? But that only occurs at that one key point, and so I never bother myself showing students how to use that one, but some of the other teachers are, depending on the school, so we'll do that ourselves. We'll put it in here, and so and that's all that's going to happen. In through the vertex, out through the vertex. And I'm going to move this out of the way. And yep, this rule works in either direction. Why wouldn't it? So it works in both directions. And there you have it. These basic rules will allow you to ray trace in any mirror. Now we're going to look at images in curved mirrors, and you will recognize some of these. Every child in human history, when they lived in a country that had breakfast cereals and spoons, knew that if you look into the bowl of a spoon, your face looks upside down. But if you turn the spoon over and look at it from the backside, your face is right up. And you've probably seen numerous reflections when your face is upside down. Now you're going to be able to demonstrate it. first thing we're going to do is mark that focus. 3.5, right there. Halfway between the center and the vertex. And then we can mark the spots using these. And what we're going to do is apply those couple of rules one after another to prove this. Best bet for this is to do the beam of light going through the center first. Remember, beams of light are leaving this object in all directions. There is no place in the room that you can't see an object unless something gets in your way. So we're going to send the first beam right through the center here. And it's important to make it accurate. These are scale diagrams. They're not sketches. Okay? That's our first beam. Now what does it do? It goes in and it goes straight back. I'm going to lighten this one up a little bit because we don't want to confuse the beam going in with the beam going out. And the beam that bounces back will come right back at you. And that's the outgoing beam. Okay, I'm going to make it thinner. And I'm going to make it quite vibrant so we can see it. That's the first reflected ray going out. Now what's the second rule we can apply? The second rule is any beam of light that goes into the mirror parallel to the principal axis will bounce out through the focus. So this one isn't going to be body blocked with another light beam on top of it. But I'm going to make it gray, and I'm going to make the reflected ray go right back through the focus. And that's going to go right here. Try to get it right through the middle of the focus. Beef it up. And I'm going to choose another... yeah, I think I can tell that apart from the others. And I'm just going to try to... Oh, I need to get those drop shadows in there. It helps my eyesight quite a bit. So I can take the drop shadow off the graph. Okay, notice right here, two outgoing beams passed through that point. This is really important here. We zoom in. We have to understand something. Being struck by the original light from the object isn't the reflection. We're tracking the reflected rays, the ones that bounced off the mirror. And this gray one was on its way to the mirror. This one is on its way out, and this blue one is on its way out. So two outgoing beams of light came together there. They both came from the tip of the arrow. They scattered, but the mirror forced them back together. And that is a condition for an image. Now, what's the third one? It's the reverse of this guy. We go in through the focus like this. And that will now bounce out parallel. And again, I'll make the incoming rays lighter in color so they don't confuse us. And that one would leave straight out. Hold the shift key down. You come straight out. Okay. Now, what do we have here? All three outgoing beams converged on that spot. That's where the image is located. Now, what part of the image is located there? Well, that's the arrowhead is located there. The tip of the arrow, all the light here that went into three separate directions, when it was coming out, momentarily came together at that spot. Well, the bottom of the arrow, its image is going to be on the floor. Any mirror you've stood in front of, your feet are at ground level in the image too. So this image has actually turned itself upside down. We could ray trace the bottom of the image, but it's really boring. think about this. If a beam of light left the bottom of the image and went to the mirror, it satisfies all the rules at once. It's going in through the center, out through the center. It's going in parallel, out through the focus. It's going out through the focus, back parallel. The horizontal axis, all the rules at once apply. So we've got the image right there. I'm going to shrink it down a little bit so we can see the arrow. And let's make it, oh, I don't know that color. There's the image. That explains why you see your face upside down in the spoon. How do we describe this? We describe it like this. What does this mean? We say this arrow was located farther away from the mirror than point C. And when we looked at the image, we noticed 4 things about the image. It was smaller than the original. The attitude means are you right side up or upside down, not like optics sucks, not that kind of attitude. The image is inverted or upside down. So in this case, it's inverted. Because I wasn't thinking while I typed because of all the glitches. Now, where did the image get located? You could measure it to the millimeter, but it doesn't matter here. We can just say, oh, the image is really close to the mirror between C and F. And what does real mean? This is the hardest part to teach you in remote environment. If you stare at that mirror, if you're in the room with it and you look at that curved mirror, it looks like a crystal ball. It looks like it's bulging out at you enough to make you cross-eyed. In practicality, it means if the big arrow was the sun, that little arrow there, if you stuck your hand where that focus is, it would burn your hand. The image looks three-dimensional, like a hologram. And unfortunately, there's no way for me to show you that here. So this is your spoon when you're long way away from the spoon. Now what happens when we get closer to a curved mirror? Well, what's the next closest spot we could make? Well, once again, I'm going to put my thing on here. I'm not going to bother moving the labels around. And we say, what happens if I got in closer to the mirror? What would be closer? Well, if we were talking about beyond the center, we could move our arrow right to the center, like that. And now we can apply the rules. Notice, though, one rule can't be used. There is no way for a beam of light to leave the tip of the arrow and go through the center and somehow strike the mirror. So one of our 3 rules is gone. We can only apply 2 rules. I used to think that would make the image dimmer. But you got to remember, there are an infinity of rays heading for that mirror. We're only tracking 3 of them. Just because one of them is missing, there are still gajillions of others. We just want the 3 that don't involve us doing math. So in parallel, out through the focus. We can do that one. The next one would be in through the focus and out parallel. And it will come close, but by no means will it be perfect. It's not possible in a diagram to get this much better than I just drew. Okay, it's in very, very close, but not quite. If you were able to set this up this way, the image you're going to get is just upside down. It's going to create an image that is equal and opposite on the other side. Why didn't it exactly work out here? To make this diagram work out, you need super accuracy for it to land exactly where it should. What would this look like? This would make you look like a face card in a deck of cards, like the king or the queen. You would be reflected. A person near you or standing behind you would go, dude, there's an upside down version of himself. In class, what I do instead of an arrow is I set up a candle. And then students standing at a distance looking at it will see a candle burning upright and an upside down mirror image of the candle below that looks dead real, and it makes it look like I've got a dual-ended candle burning in the classroom. Alas, we're remote. How would we describe this one? Like this. And it's still what's called a real image because real beams of light collided there. And I think you see where we'll go next. I put that on there, and we were out here, then we went to this spot here. We went to this spot. Now we'll go somewhere in between. And this is where the brain benders begin. First off, this one's not going to work so well because the mirror is too tall in the diagram. In real life, anyone giving you a curved mirror this big, you get clown forehead distortion at the edges. In real life, if we want to make a precision mirror to make images, you can barely see the curvature. Your makeup mirror is one. If you feel the surface of the magnifying end, it's curved, but very gently. If you have a larger mirrored surface with a bigger curve, it starts to screw up at the edges. At first, it would seem like there is no way to go from the arrow tip through the center and strike the mirror. And a lot of students assume they can't do the first rule. But I'm going to ask you to think about the geometry of this situation. If I do this, and I make a line like that, trying to get it so it goes right through the center and the tip of the arrow, and it strikes the mirror. Does that dotted line going through the center not strike the rim of the mirror exactly at 90 degrees? It's a diameter. So there is a path. It's not that the light has to go through the center. The light has to be on the same path that would make the ball kick straight back. And once again, let's think of this logically. If I took you into a room and we did this, I said, here, we're going to play ball in this room. I'm setting up this big room, and you're going to stand here at the center, and you're going to kick a ball straight out, straight to the wall. You know it's going to turn around and come straight back at you. But what if I said this instead? You know when you kick the ball at the wall just a bit ago? I wonder what would happen if you took a couple of steps forward and then kicked it straight at the wall. Would anything change? Or would it still come straight back at you? Nothing has changed. If a beam of light started here and followed that path to the mirror, it would bounce straight back. So any ray of light that left the arrowhead and followed that same angle, it guarantees it strikes the mirror at 90 degrees and it goes straight back where it came from. And this is perhaps one of the hardest ones to understand, and you need a pale dotted line on there to convince yourself of it. So there it is, straight in, straight back. It didn't really ever have to go through the center. The center just gives you the path of like the spoke on the bicycle. That's the hardest one. The other two are easy still. If we do this, straight in, it will leave through the focus. Okay? And if you went through the focus, it's going to come out parallel. This one here, and this is the beam that won't work too well. If you go that way, it's going to leave parallel. Now, you notice the big miss. Why did it miss? Because we're using too much of the mirror. So there isn't a clean miss. This should be down here really. Because the diagram is too large, right, it won't work. This line should have come out down around here. And it didn't. Well, why would I give you something like that? Imagine I made this mirror diagram for you and I only made it halfway above and below these lines. You'd have to zoom in so far. So we can ignore the fact that it didn't line up. What we've got is a freaking huge image in the mirror now. The image is upside down and it's freaking gigantic in the mirror. Objects located between C and F makes an image that is further beyond than C. And what did we call this now? Well, obviously, the size is equal to huge, attitude equals inverted, location equals beyond C, or we can use the greater than sign, and the type is equal to real. When would you see that? Not too often. If you approach a curved mirror and you start getting closer and closer, you'll be upside down until at a distance from the mirror your head gets huge and just distorts out. if you have a magnifying makeup mirror at home, to see this effect, you have to stand well back of it, like clean across the room, and you'll see yourself upside down. And as you walk towards the mirror, you'll get bigger and bigger and bigger and bigger. But the makeup mirrors, you need to be quite a distance away to see this effect. All of these would have been demonstrations in class. The next one is now to move directly on top of the focus. What happens if we put this right there? Well, I think you recognize now this effect. If you can connect a line from the center to the mirror that passes right through the center like that, then a beam of light can do this. It can leave and strike the mirror, and then it ricochets backwards like this through the center. And the next one, straight in, like that. And then it will pass out through the focus. Like that. When will these two beams ever cross? Or are they parallel like choo-choo tracks? These two beams came out parallel. And you don't make a painting by taking light from the tip of a person's head and putting it on two different locations on the canvas. This is what you see on police helicopter searchlights. There's no focusing of the beams anywhere. It sends out a circle of light. The bat signal, helicopters in flight, the spotlights that sweep the sky, they put the light bulb right at the focus and it generates parallel rays. The lights the dentist put over your head, you notice there's something blocking the middle because they're sending the light up to the mirror and it's bouncing it back at you. This is a spotlight. And this diagram is very hard to work out correctly. Notice there was a beam we couldn't draw. We couldn't draw any beam of light from the... What happened? That's interesting why it jumps slides. Notice there's no way to go from here through the focus and hit the mirror. And this is where some teachers use that third rule. I just can't be bothered with it. And they'll do this. And they'll go, looky. When I apply the rule through the vertex, I get the same thing. I get a third parallel beam. But we don't care. We're not into that kind of detail here. Even that third rule now works out. And the last one, the hardest one of all, is what you see when you get your normal viewing distance from a makeup mirror. Once you decide to be foolish enough to get closer than the focus to a mirror, I'm going to shrink this guy down a little bit because it'll be too big. Now, this one has two of these shots that you have to set up the dotted line first. It's quite possible to do this one. And it's also possible to do this one. And this takes a little bit of brain power to understand what's happening here, and not something I would test you on. This beam of light that went in, if it went in here, it would come straight back. So we expect this. Any beam of light that went that way, according to the rules, would turn around and go right back out. Like that. Okay? And any beam of light that went in this direction, like it came from the focus, is obligated to bounce straight out. Like that. And finally, any beam that goes straight in is obligated to reflect through the focus. And now we're like, these will never converge. They're spreading out. But once again, if I hid information from you, think back to the triangulation slide. If I just let you see that, could you backtrack those arrows to where they would converge mathematically? Not in reality, because they aren't converging, they're spreading apart. But could you follow them backwards to where they seem to have come from using that triangulation technique? Well, let's see. I'm going to slide this over a little bit so we can't see the object. Now we got a good look at these three lines. So let's follow them backwards as far as we can. I'm going to line that one up there. Like that. I'm going to put another one in here. Like that. And I'm going to take another one here and follow back so it lines up there. And look how close we came to an intersection. Let's take this away now. The three scattered rays look like they came back from here. They didn't perfectly line up. It's really unlikely that diagrams of this size line up. But what we've got now is an intersection point. They didn't quite make a complete intersection. It's a triangle intersection. Like they closed up here, here, and here. So a lot of times we just tell the students to put it somewhere in the middle. But you see where those three lines wanted to come to a convergence. And there it is. What do we have now? This is the makeup mirror. Girls, you should smash them. Those mirrors that magnify your face and increase your self-loathing and you're like, I suck, I don't like it. Whoever invented those should burn in hell for the lack of confidence they give you. That you can examine your face at microscopic detail just so you can find flaws to feel bad about. Don't do that to yourself. You're awesome. Why do we call this a virtual image? Because the image is behind the mirror. It doesn't pop out at you like a hologram. And the most important thing is you can't project it on the wall. Again, there's a demo in class I do. I can show you some videos of it, but it doesn't look the same as a video versus reality. If you get a real shiny bowl and look down inside of it, even not a mirrored one, it can be a glass bowl, anything with a reflection. You look into a glass bowl from a distance, it looks like your face is bulging out of the bowl upside down. But if you get close enough to the makeup mirror, it will turn your image right side up and make it huge, but it looks very flat because it's behind the mirror. If you stand at a huge distance, like you've never stood before from your makeup mirror, the image will flip upside down and the mirror looks like it's bulging out at you. You have to try it to see this effect. Images that are produced by scattered rays cannot project on anything. This mirror here would create, at this range, would create a tiny, extraordinarily bright image of the main object, and it would project on a sheet of paper. At school, I would take you outside, aim it at the sun, and chunks of wood would burst into flames. This one cannot project. Why not? Because in order to make artwork, you have to copy all the light from the tip of the object you're staring and put it at one spot on the page. This position now, the mirror is taking the light from, say, the tip of your nose, and it's scattering it across your bedroom wall. It won't image on the wall. You won't see it like a movie projector. But your brain is smart enough to go, I don't care if those rays are scattered. Your brain can backtrack them and give you the impression of something on the other side of the mirror world. And that's how these mirrors work. And what we're going to do next is we're just going to focus, no pun intended, on some real uses of these mirrors since we can't do the labs associated with them.